My name is Andreas Kristiawan, and today I would like to explain you about our study case. So our study case is about floods prediction system, and the background about that is floods cause severe damage in many regions. Data from rainfall sensors, water levels in rivers, and weather forecasts are available, but the prediction is not fully optimized. And that case often happen in our country, Indonesia. And based on that background case, we also took some key variables. There are rainfall intensity, rainfall duration, river water levels, river trend, historical floods records, and also the vulnerability of the area. And based on that key variables, we have an objective to create a flood early warning system that process incoming data to predict floods and also send timely alerts to the communities. But from that objective, we also have some challenge that we need to face. There is, we have to create a flood early warning system that are fast and accurate, but the potential risk is the data can be messy, missing, or noisy.
Hello there everyone, my name is Bana Farhan Atala and I'm going to explain the decomposition. First off, we will collect data from that rainfall. Thus we will monitor river water levels and relative historical flood from the area, and prediction modeling, and we will we will apply time series analysis to detect river water trends, train machine learning models to predict the next flood, and alert distribution, and we'll collab with ISP to give out on-time emergency alert in smartphone when the risk of flood is high. We will collab with news weather forecast to send out radio and TV broadcasts about potential risk of flood, and using official social media accounts to give out updates when a flood happens. And for the system improvement, we will evaluate on the accuracy of the past prediction, and we will collect community feedback and enhance the communication channels for wider reach, and we will improve the models by returning the new data.
So in this part, we focus on recognizing patterns that can help predict when floods are most likely to happen. For example, when rainfall intensity is high and the river level keeps rising, it clearly shows that the flood risk is increasing. If both variables go beyond their threshold, meaning it's raining heavily and the water level is high, the system will issue a flood warning. Another pattern we noticed is the upstream and downstream effect. When upstream areas start flooding first, the downstream areas will usually be affected not long after. We also used historical flood data since areas that have flooded repeatedly under similar weather conditions are more vulnerable. Basically, by recognizing these patterns, our system can detect early signs of flooding and send alerts before the situation gets worse. Next is the data representation and abstraction part. Here we identified which variables are essential for flood prediction and which one can be simplified or ignored. The critical variables we focused on are rainfall intensity and duration, river water level and trend, historical flood records, and the vulnerability index of each area. These variables are the main inputs used to calculate the risk level. On the other hand, non-essential data like wind speed, humidity, or socioeconomic factors are not directly related to predicting floods, so we exclude them to keep the system simple and efficient. In short, data representation help us understand what information really matters, while abstraction help us focus only on what's relevant to solve the problem accurately.
Hi everyone, my name is Atala Haryaputro, and today I will be presenting about the input, calculations, and output of our flood prediction and early warning system. First, let's start with the input. To predict floods accurately, we need several data such as rainfall intensity, rainfall duration, river water level, river trend, historical flood records, and vulnerability index. Next, in the calculation stage, the system processes all this input to calculate a risk score ranging from 0 to 10 and the probability of flood in percentage. It also performs threshold comparisons, which means checking if the rainfall or river level has exceeded the safe limit. Finally, for the output, the system gives the risk level low, medium, or high and sends flood warning alerts through text message or sirens, along with the recommendation actions like stay alert, prepare, or evacuate.
My name is Andreas Kristiawan, and I would like to explain you about this slide. So the algorithm that we use to solve our study case is called greedy algorithm. What is greedy algorithm? The greedy algorithm is the system that can make a quick decision based on the current situation. For example, if there is a rainfall and after that the threshold and river level is rising fast, so the system will immediately issue a warning. So there are also some reasons why we choose that algorithm. So for the first one is fast. That algorithm can enable real-time alerts. And the second one is simple. The algorithm only checks the most important conditions. And the last one is effective. That algorithm makes immediate decision without waiting for the less relevant data. And based on the three reasons, we decide that greedy algorithm is the best immediate option to minimize risk, which is crucial for an early warning system.
Hi everyone, my name is Atala Haryaputro, and next I will explaining about the flowchart. So it starts by taking the input data such as rainfall intensity, rainfall duration, river water level, river trend, historical flood records, and vulnerability index. Then the system calculates the risk score, the probability of flood, and checks if the values go beyond the safe limit. After that, it determines the risk level, low, medium, or high. If it's low, the system will tell people to stay alert. If it's medium, it will suggest to prepare and monitor. And if it's high, it will send a warning alert and recommendation to evacuate. Finally, the process ends after the proper action is taken.
Good day everyone, I'm Mr. Novrijon. My name is Pertia Anissa and I'll be presenting our study case about a flood risk detection system. Our pseudocode starts with the input process. Here, the system receives several key data values, such as rainfall intensity, rainfall duration, river water level, river trend, historical flood record, and the vulnerability index of the area. These 6 inputs represent both current weather condition and past data, which are all essential to evaluate the flood situation accurately. After that, the program calculates the total risk score and flood probability. This risk score is a numerical value that summarizes how likely a flood might occur based on the combined data. Once the risk score is calculated, the pseudocode uses conditional statement or if-else logic to classify the situation into 3 risk levels. Now, let's move on to the Big O analysis of our algorithm. The purpose of Big O notation is to describe how efficient an algorithm is. In other words, how fast it runs as the amount of input data increases. In our flood risk detection system, the algorithm performs only a fixed number of steps. It takes 6 inputs, does a few simple calculations to find the risk score and flood probability, and then check the result using a few if-else conditions. Because every step happens only once, and there are no loops or repetition, the total time needed to complete the program never changes. No matter how many times it runs, or how large the input values are. As shown by the table in the right side, this means our algorithm has a constant time complexity, written as big O of 1, or O open bracket 1 close bracket. In simple terms, the algorithm always runs at the same speed. It gives result instantly.
Hello there everyone, my name is Bana Farhan Atalah, and I'm going to explain to test the algorithm that we make. So first off, we have 3 test cases. The first one is the safe one, the second is the medium risk, and the third is high risk. For the safe test case, the rainfall intensity will be around 5 millimeter per hour, and the rainfall duration should be 1 hour, and the river water level should be around 12 meter, and the river trend is stable, so it's not rising, and there's no historical floods whatsoever, and so the vulnerability index should be low, and because of that the flood probability is very low. For test case 2 medium risk and test case 3 high risk, it's higher than the test case 1, the safe one,